So here's the idea, guys. We're starting what's called the quantum wave mechanical model of the atom. Of the hydrogen atom. So here's what Bohr's model of the hydrogen atom did. It assumed with 100% accuracy that you could predict the position and the momentum of an electron. What does Schrodinger say about that via his cat? You can't. You can't know for sure the position and the momentum of the electron. Okay, but he doesn't know that because Schrodinger hasn't come up with that theory yet. Okay, he says that electron orbits the nucleus in perfect concentric rings. Okay, and he says that you can calculate the energy of the orbits and therefore the electron and the quantum of energy released or absorbed when the electron moves up or down energy levels. Does this all sound like the test that you guys just took? Yeah, that you guys just did so awfully wonderful at. There, I used two adjectives. One of them might be right. Aha. We'll find out. Okay. Like I said, do you need to write this down?
Yeah.
This is no. You do not need to write this down.
No,
This is stuff you know, right?
wait, why can't we click on the PowerPoint?
Because I'm a jerk. Okay. There were a couple of holes in Bohr's theory that I think I alluded to in the last chapter. I think I actually directly said them. He didn't address how a negatively charged electron could hop around without falling into the positively charged proton of the nucleus. All right, which isn't as big of a deal to me as he didn't actually explain the spectra given off for any of the elements except for hydrogen. His equations, his mathematical equations only worked for hydrogen, which kind of makes it kind of a flop of a theory, right? Sounded like a good idea at the time.
Besides hydrogen.
Some people think that Heisenberg is a dude from that drug show.
That drug show?
That drug show.
Bullshit.
It's like that 70s show, right? Breaking Bad, right? Heisenberg's not a guy from Breaking Bad. Heisenberg is a guy who came up with this uncertainty principle that says that it's impossible to know at the same time the momentum and the position of a particle like an electron with 100% certainty. So this is, Heisenberg actually helps Bohr out by saying, hey, Bohr, it's not a big deal that you could only do hydrogen because you know what? We can't actually know the energy and the position of the electron at the same time. So he's saying, hey, Bohr, you think you know where the electron is? You don't know its energy. That's why your equations are not working. So no, I've not been lying to you. You can do it for hydrogen because it's not as complex. But as soon as you get another electron, it's impossible to know both the speed, the energy, and the position of those electrons.
Excludes hydrogen.
Okay, this excludes hydrogen. Yes. Okay, so for hydrogen, we can know reasonably certain enough that we can call it 99.99% certainty. But Heisenberg says that we can't do it for anything else. Now, what that means here, we'll recap here. Actually, we'll recap. We'll preview. Preview is the word. Here, okay. So we're going to be talking about the quantum mechanical model in this chapter.
All right.
Okay, and here it is, side by side with Bohr's model. Bohr's model says that energy is quantized. Energy comes in specific packets, right? Okay. The quantum mechanical model agrees with that. Okay. Bohr's model says that electrons can transition from one position in an atom to another position in an atom, and that's going to be what causes photons to be given off. The quantum mechanical model agrees with that. Bohr says that the energy of an energy level is equal to negative 1312 kilojoules per mole over n squared. Remember that one? That oldie but goodie? Hey, guess what Schrodinger says? That's not right. Only works for hydrogen. Okay, Schrodinger works out a wave equation, which works fairly nicely. I'm going to show you the Schrodinger wave equation on the next slide. Okay, it's actually in your textbook if you want to look at it also. And then finally, Bohr says that the electrons are in circular orbits. Schrodinger says, you know what, let's add a couple letters to that because orbits isn't right. So Schrodinger says, for the quantum mechanical model, electrons are in something called an orbital. It's not a sphere necessarily. Okay? And he's made basically what are called probability maps. He uses the math to produce 3D. You guys know the Cartesian coordinate system, right? X and Y. What happens if you want 3D?
What?
Yeah, you have to add Z, right? So you got X, Y, and Z. He does a three-dimensional probability map of what these orbitals look like, and that's one of the things that I gave you on the handout, what the orbitals wind up looking like. Okay, so we'll get to that in a few minutes. The math. So guys, here's a three-dimensional map, right? This is a three-dimensional map of his probability map of what we call an s orbital. And this is the math that you guys don't want to play with. That's the puppy. Okay. There are puppies. You don't get to play with the puppies. All right. You don't want to do this math. Okay. Heisenberg said we can't know the energy and the position of an electron at the same time. This probability map that's on this slide here shows the probability of finding an electron in a given amount of space. So each of the dots that are on that map represent a probability of finding an electron there. Where's the highest probability of finding an electron? Okay, the highest probability seems to be right about here. Where's there lower probabilities? Well, here's lower probability, there's lower probability, there's some lower, right? Where is there definitely no probability of finding an electron? I see no dots out here. Okay, bad probabilities way the heck out here of finding electrons. Okay, so basically what Schrodinger's done is he's made up a three-dimensional map of where the electrons are most likely to be found 90% of the time. Electrons are found in this sphere-like shape. Okay, and all right, so I told you guys that on the last slide that the wave equation solves for those three-dimensional shapes. It also gives us some other information that's hidden within that three-dimensional shape. Okay, so the electron, things that we can know about the electron by the Schrodinger wave equation is, number one, we can know how much energy it has. Okay, we can know the shape of the orbital. Refer to that handout that I gave you guys. The 4 different clusters of shapes: spheres, dumbbells, cloverleafs, and funky shapes. We can also know the orientation in space, which way it's pointed. And then lastly, we know which direction the electron is spinning from this equation. We can x-axis, y-axis, z-axis for orientation. Sorry. All right. I don't think we need to spend any real time on this definition slide. Probability map, you guys know what it is, right? You guys have seen the probability maps. Orbital, by definition, if you didn't write it down, by definition, the electron has to be within that orbital 90% of the time. And then finally, we're going to label orbital types S, P, D, and F as we go along here. And there are actually more than those 4. Those 4 are what you're going to be tested on. There's a G, there's an H. We'll do a little bit of practice with G and H. But I don't have pictures of G and H for you. So here we go. All right, we're ready to do some quantum mechanics. Now that we've got those definitions down. Okay. Ooh, hey, you know what, guys? This is actually the notes on the front of the handout.
Really? Oh.
All right. So you've got to know about what a principal quantum number is, what the angular momentum quantum number is. You got to know the magnetic quantum number and the spin quantum number. Okay, I made that up to kind of organize the information for you. So here's the definitions. So the first thing you got to know about is the principal quantum number. The principal quantum number is abbreviated with a designation of lowercase n, and it's going to describe the size and energy of an orbital. Okay. The second item is the angular momentum, designated by a lowercase l, usually written as a cursive because you don't want it to get confused with a 1. All right. It's going to describe the shape of the orbital, which is those S, P, D, or F shapes we were just talking about.
So that goes from possible.
The third item that you need a meaning for is the magnetic quantum number, which is abbreviated M subscript L, or M sub L. Don't ask me why. It describes the orientation of the orbital in space, the direction it points. Is it on the x-axis? Is it on the y-axis? Is it on the z-axis? Or is it on one of those complicated axes that are the d and the f orbitals? Okay. And then finally, there's something called the electron spin quantum number, which is M sub S. And it describes the spin of the electron inside the orbital, which direction the electron is spinning. Okay. Like I said, lots and lots of information. We're going to start making sense of it in a little bit here. We want to know what are the possible values, right?
Yeah.
Okay, so possible values. N, just like with Bohr's model, N starts with the first energy level. It moves on to a bigger energy level labeled 2. It moves on to a bigger energy level labeled 3. And it continues on until infinity. Okay. L, the orbital shape, can have numbers attached to it. L always starts with 0. And it can continue on until n minus 1. So infinity minus 1 would be the last L that we could write. Typically, guys, we don't deal that high. We usually, go as high as n equals 6 and don't go any higher than that. So your biggest L is probably going to be 5 because the biggest n is 6.
We arbitrarily choose +1/2.
All right. So M sub L talks about the magnetic quantum number, and it can go from negative L to positive L and include 0. So if my L says that it's 5, my M sub L would go from negative 5 to positive 5.
What? Yeah.
These are all attached to each other. So here are the examples that I've been giving. I said, okay, we're going to say that n is equal to 6, right? So we're going to say that that's going to be the biggest one we'll use because I don't think you guys want to deal with n equals infinity, right?
No.
Okay.
L equals
So
5.
then my L would equal n minus 1, which is 5. Okay. That means that my M sub L should have values that go from negative 5 to positive 5, and 0 is an option in between. They're going to be integers. So technically speaking, what I should write down is negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, and 5 as choices for M sub L.
So those are an example.
This can go in as an example, sure. And then finally, there is the spin number, M sub S. M sub S was chosen arbitrarily. It either has a value of +1/2 or -1/2, depending on which of the 2 electrons that we're talking about. There's only 2 electrons allowed in each of those orbitals. So in M sub S equals +1/2. would be a fair thing to say. Of course, we could also say m sub s is negative 1/2. Those are my only two choices.
Always, no matter what.
For m sub s, they're always my only choices.
You're forced to do
Oh, okay. We arbitrarily choose plus 1/2 to designate a spin that's read as clockwise. I know that doesn't look like clockwise, but that's up. And m negative 1/2 always represents a down or counterclockwise. Or for those of you guys who like the phrase counterintuitive, counterclockwise. Anti-clockwise? Anti-clockwise. Ooh.
So we random
All right, so talking specifically about the principal quantum number, guys. The principal quantum number talks about size and energy of an orbital. I'm going to go quick here. Again, this is review. And it can be 1, 2, 3, 4, 5, can go all the way up to what number? Infinity. All right. And beyond. It cannot be 0 because there's no such thing as a 0th energy level. Okay, it has to start with 1. And here's the rule for it, guys. As n increases, as this number increases, the orbital size gets larger, and the electron spends more time farther from the nucleus at a higher energy. So if I'm trying to compare two electrons, and I know that one is n equals 1, and I know one is n equals 6, which one has more energy?
Beat yourself.
All right. If I'm trying to compare two electrons, one is n equals 1, and the other is in n equals 6. Which one has more energy? Yeah, n equals 6. Okay, so this should be a logical thing. Okay.